Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. In the last lecture, we discussed largest element of a set. In today's lecture, we are going to discuss an important example, important problem from the book Principles of Mathematical Analysis by Walter Rudin. The problem is that we need to show that there is a set that consists on all rational numbers and the rational numbers are positive, whose square is less than 2. Here the set A consists on all positive rational number whose square is less than 2. We need to show that this set has a no largest element. Uh, how we will prove this problem? We suppose on the contrary, there is a largest element P of this set. And for this P, we can find another element Q of this set that is larger than P. So we assume that, on the contrary, we suppose on the contrary that P is largest element, P is largest element of A. If P is largest element of A, then every element that belong to uh, this set A will satisfy three conditions. The first condition is that element should be rational. So if P is the largest element of A, then it will always belong to this set A. This is the definition of the largest element. So when P belongs to the set A, then P has three characteristics. Firstly, P will be rational, that is P belong to Q. Further, P will be positive. And the third and the last condition is square of P will be less than 2. So every element that belongs to this set always satisfies these three conditions. We suppose that on the contrary that P is the largest element of A. To prove the result, to prove the result, we can find a number Q. A number Q such that Q is an element of the set A also, and Q is greater than P. In this part, uh, we have supposed that P is your largest element. However, it is large. For any P of this set, we can find another element Q. And for this Q, I have two claims. My first claim is that Q is an element of A and Q is also bigger than P. When Q is bigger than P, then it will show that P is not largest element. That is our supposition will wrong. So how we will prove this? We will find a value of Q. We put here a Q with the help of P. So we find Q. Here we make Q with the help of P, where P is a rational number and belong to the set A. We find Q is equal to P minus P square minus 2 over P plus 2. Can any other value of Q will work here? Yes, it may be possible that there are so many values that can we take here. For example, one of the value that I have observed rather than this value, you can take Q is equal to P minus P square minus 2 over P plus 4. Suppose uh, I have observed some uh, results from this set A. Your nominator should be P square minus 2 because due to this inequality, here x square is less than 2. This gives us x square minus 2 less than 0. So this expression must should be involved in denominator. Suppose if one if someone write here p square plus 2, then such value of q will not work here. So it may be possible you can find any other value, but I am using here this value already written in your book. So we are going to put q is equal to p minus p square minus 2 over p plus 2 here. Next, I will prove my first my one of the claim q is greater than p. For this, as uh, because p is the largest element we have supposed of set A. So p square will be less than 2. If p square is less than 2, then p square minus 2 will be less than 0 here. It means p square minus 2 is negative. And what's about the denominator? Because your p is a positive rational number, when you add 2, that is also a positive quantity, the denominator will always positive. So this is negative and p plus 2 is positive. Your final answer will be less than 0. This shows that this fraction will be negative here. So we can write q is equal to p minus some negative quantity. Some negative quantity. When we multiply this negative quantity with negative sign, this will give us some positive quantity. This will become some positive quantity. P plus some positive quantity here. Now, as Q is the sum of two, P is already positive. So P belongs to this set and this set has all positive rational numbers. So obviously P is positive rational number. This is positive and this is also some positive quantity, and Q is the sum of two positive quantity. This shows that Q is always bigger than P. Suppose H. As 5 plus 3 is greater than 8. 5 is positive, 3 is also positive. And 8 is the sum of these two parts. Can I take 8 is greater than 5 individually, and 8 is also greater than 3. So, in the similar manner here, because Q is the sum of two positive quantity, so individually Q will be greater than P, and Q is greater than this some positive quantity. So, this is our first claim that Q is bigger than P. Next, we will show that Q is also the element of this set A. This is our first claim. So, uh, as say this is one, as P is greater than 0 by definition of the set, and Q is greater than P, this implies Q is greater than P and Q is greater than 0. This shows that Q is also positive. Say this is 2. Next to show that when Q will belong to the set A, Q will belong to the set A when Q will satisfy the three characteristics. First characteristics, Q belong to Q, that is Q is rational number. Second characteristics, Q should be positive, that we have proved here Q is greater than 0. And the third one, q square less than 2. Then we will say that q is also belong to A. Every element of set A has three characteristics. One is that, first is that it should be belong to set of rational number. Second is it should be positive. And third one is its square is less than 2. Uh, this property we have proved q is greater than 0. Next we show that q is also a rational number. For this we can give reason, as we know that sum product quotient of two rational numbers is always rational. So by definition of q, what is the definition of q? Small q. Our q is consist on p, that is rational number, minus p square minus 2. The square of a rational number is always rational. Rational minus 2 is always rational. Divided by p plus 2, that is again a rational. Rational over rational is always rational. And the difference of two rational is always rational. So as sum or difference, product quotient of a rational number is always a rational number. So by definition of q, this implies q belong to q. This fulfills the second condition of this set, q is rational number. Now we prove third condition, that q square is less than 2. For this we consider here consider by taking LCM here, this will become p into p plus 2 minus p square minus 2 over p plus 2. This will give us p square plus 2p minus p square plus 2 over p plus 2. Here p square will cancel with p square. This will become 2 times, by taking common 2 from these two terms, p plus 1 over p plus 2. As we have to show that q square is less than 2, or in other words, I have to show that q square minus 2 is less than 0. For this, by taking square of q, we have q square is equal to 4 times p square plus 1 plus 2p over p square plus 4 plus 4p. Next, by subtracting 2 on both sides, this gives q square minus 2 equal to 4p square plus 4 plus 8p over p square plus 4 plus 4p minus 2. By taking LCM, we have 4p square plus 4 plus 8p minus 2p square plus minus 8 minus 8p over, we can write it as again, this is the actually p plus 2 whole square. By cancelling out 8p with 8p, and from 4p square minus 2p square, this will give us 2p square plus 4 minus 8, this is minus 4 over p plus 2 whole square. By taking 2 common from the numerator, we have uh, p square minus 2. So this will become q square minus 2 is equal to 2 times p square minus 2 over p plus 2 whole square. Next, as uh, it is given in the assumption that p square is less than 2, this shows that p square minus 2 is less than 0. P square minus 2 is less than 0. The denominator p, this is p plus 2 whole square. P is positive rational number plus 2 is also, p plus 2 is also positive rational number, and its square will always positive quantity. So numerator is negative, denominator is negative, denominator is positive. The final fraction will be less than 0. This implies q square is less than 2. Say this is, I think this is 4. So by combining all z from 1, 2, 3, 4, we have q is greater than p, q belong to rational number, q is positive, and q square is less than 2. This shows that these three characteristics shows that q belong to A. So q is the member of this set A, and p we have supposed was the largest element of this set, but we have uh, found here another element q that is also greater than our supposed largest element. So our assumption is wrong. Hence, this set has a no largest element. So I hope today's lecture was helpful for you. In the next lecture, we will discuss the same problem, but in that problem, the difference is only that x square is greater than 2. In that case, there is again a set. Suppose its name is B, and B is a set of all positive rational number whose square is greater than 2. And for that set, we will show that that set has a no smallest element. So, inshallah, we will meet in the next lecture. Okay, take care. Allah Hafiz.